Today we are going to be taking a look at what is called the Binomial Theorem and Pascal's Triangle. So recall that a binomial is a polynomial that has two terms. In this section we're going to be learning a method for a binomial expansion when a binomial is raised to a whole power. So let's review what we already know about raising a binomial to a whole power. So I know that this means x plus y quantity squared is the same thing as x plus y times itself. And if we FOIL that out, distribute it out, however you like to say that, x times x is x squared, we have an x times a y term, we have another x times a y term, and then we have y times y, y squared. And don't know why I put that. This is the same as x squared plus 2xy plus y squared. And that is the expansion for that binomial squared. What if we had this binomial to the third power? Well, that would mean x plus y times itself 3 times. And that means I can take one of the x plus y's and multiply it by what we got for x plus y times x plus y. And I'm going to distribute this now. X times x squared, x times 2xy, x times y squared. And now I'm going to go to the y term. Y times x squared is the same as x squared y. Y times 2xy is 2xy squared. And then y times y squared is y cubed. And we can combine like terms. Oops, that was y cubed up there. X times x squared is x cubed. We can combine like terms now and we get x cubed plus, okay, here is an x squared y term, and here is an x squared y term, so I'm going to combine those and make 3x squared y. My goodness, okay, I can see that I made another mistake here. This golly Moses, I really butchered that. X times y squared, I have no idea why I put that, but I just didn't write the y. X times y squared is xy squared. I just didn't put the y there. Oh, I don't have any idea why. Oh, I'm just going to keep this though. I could redo this video, but I'm not going to. We have xy squared plus 2xy squared. I combine those to get 3xy squared plus y cubed. So the process gets longer and longer as the exponent increases. Okay, can you imagine expanding this one here? Now I will say this though. What's really tricky about it is not really the x and the y parts. What's tricky about it are the coefficients. Let's look at the pattern here. I'm starting with an x cubed, and then I have an x squared y to the first, and then I have an x to the first y squared, and then I have a y cubed, right? So if we had x plus y to the 8th, what do you think that very first term would be? It would be an x to the 8th plus. The next term would have some coefficient, I don't know what it is, but then what would the x's and y's look like? The x exponent would decrease by 1, the y exponent would increase by 1. Each time their powers are going to add to 8. So the next term, don't know what the coefficient is, but I know that the x's are going to look like x to the 6th, and the y's are going to look like y squared. And that pattern would continue until the very last term where we would have no x's left and we would have only an x to the 8th. Okay, so even though I don't know what the coefficients are on all of these terms, I know what the x's and y's look like. Let's consider some expansions of x plus y to the n. And in class I'm going to give you guys some time to take a look at these expansions. And then you guys are going to tell me what patterns, what observations do you see with these above expansions? So for one of the patterns, one of the observations you would probably say are the same thing that I said up here with the x's and the y's, that each time their exponents add to the power that we started with each time, right? What about how many terms are there? In the expansion for x plus y to the fifth, how many terms are there? There's 1, 2, 3, 4, 5, 6. There's 6 terms here. How many terms are in the expansion for x plus y to the fourth? 1, 2, 3, 4, 5. So there are n plus 1. If the exponent is n, there are n plus 1 terms in the expansion. And I'm sure you guys can see some other patterns that you're going to tell me about in class. All right? Okay. Let's take a look at how we can find the coefficients in that binomial expansion for any exponent n. This is called the binomial theorem. In the expansion of x plus y to the n, the first term is x to the n. The second term, and this is one of the observations that I'm sure you noticed, the second term has the coefficient of n. In each of those, the second term had a coefficient that was the same as your power that you started with. Okay? And then we have this. And this is a way to get every other coefficient. The exponents are going... This should be a power, not a subscript. I'll move that for your notes. That should be a power. Okay? So everything else is very predictable, but this is a way to find any coefficient. All right? The coefficient of any term is n factorial divided by n minus r factorial times r factorial, where r is the exponent on the y. N minus r then would be the exponent on the x. So n factorial divided by the x exponent factorial times the y exponent factorial. Sometimes we use this symbol instead of this notation. So in the expansion of x plus y to the eighth, the first term is x to the eighth. We could use this to get that coefficient. 8 factorial divided by the x exponent factorial times the y exponent factorial. Remember, 0 factorial is 1, so that is just 1, and I have 8 factorial over 8 factorial, and that is just 1. The second term is going to be 8 x to the 7th, y to the 1st, right? So the coefficient will be 8 factorial over 7 factorial times 1 factorial, which is 8 times 7 times 6 times 5 times 4, etc. That's 7 factorial, divided by 7 factorial times 1 factorial. Well, the 7 factorials reduce out. 1 factorial is 1, so this whole thing is just 8, and that's what we got. Okay, the third term will have this coefficient, because I know that my x exponent will reduce by 1, my y exponent will increase by 1, so this is how we're going to find our coefficient. So 8 factorial divided by 6 factorial times 2 factorial. 8 factorial is 8 times 7 times 6 factorial. I'm stopping there because I know I have a 6 factorial on the bottom and I can reduce that out. I'm going to write 2, not 2 factorial as just 2. 2 factorial is 2. So the 6 factorials reduce out. 2 goes into 8 4 times. I'm left with 4 times 7, which is 28. And the third term has coefficient 28. Let's find the coefficients of these terms. X to the 5th times y cubed, that'll be the next one, and then x to the 4th times y to the 4th. So the coefficient of x to the 5th y cubed will be 8 factorial over 5 factorial times 3 factorial. 8 factorial is 8 times 7 times 6 times 5 factorial. I'm stopping there because of the 5 factorial on the bottom. 3 factorial is 3 times 2 times 1. The 5 factorials reduce out. 3 times 2 is 6. It leaves a 1 on the bottom, so this coefficient is 56. So the term will be 56 x to the 5th y cubed. That'll be the term. The coefficient is just the number in front. For x to the 4th y to the 4th, 8 factorial over 4 factorial times 4 factorial. 8 times 7 times 6 times 5 times 4 factorial divided by 4 factorial times 4 times 3 times 2 times 1. I just don't write the times 1. These 4 factorials reduce out. 4 times 2 is 8. 3 goes into 6 twice, so I'm left with 7 times 2 times 5, that is 7 times 10, or 70. So the term will be 70 x to the 4th y to the 4th. So let's write the full expansion of x plus y to the 8th. We start with x to the 8th, no y's. Our next term is 8 x to the 7 y to the 1st. My next term, we found it up here, is 28 x to the 6th y squared. The next term, 56 x to the 5th y cubed. Then 70 x to the 4th y to the 4th. And now the y's are going to continue to increase and the x's exponent is going to continue to decrease. So the next term will be y to the 5th x to the 3rd. The coefficient will be the same as it was for this one. So 56 x cubed y to the 5th. The next coefficient will be the 28 x to the 2nd y to the 6th, and then 8 x to the 1st y to the 7, and lastly y to the 8. So we expanded this very large binomial in a much faster way than it would have taken had we multiplied, and then combined all those like terms. There would have been a lot of them. Okay. All right, let's do some examples. In the expansion of x plus y to the 7, what is the coefficient of the x to the 4th y to the 3rd term? So we have x to the 4th and y to the 3rd in this expansion. Well, the coefficient will be 7 factorial over 4 factorial times 3 factorial. That will be 7 times 6 times 5 times 4 factorial divided by 4 factorial times 3 times 2 times 1. The 4 factorials reduce out. 3 times 2 is 6. I'm left with 7 times 5, which is 35. So therefore, the coefficient is 35. Okay? All right. What if it's not a plane x and a plane y? What if we have other things, which we often do in a binomial? In most binomials, we don't have an x and a y. We have an x and some number, right? So what if we have 2x minus 3 to the 5th power? We're looking for the x cubed term. Well, the x cubed term will be when the first thing, whatever it is, here it's a 2x, is being raised to the 3rd power. We'll be multiplying by negative 3 to the 2nd power, because their powers are going to add to 5. So my binomial theorem says that out here in front is going to be a 5 factorial divided by 3 factorial times 2 factorial. And that is 5 times 4 times 3 factorial divided by 3 factorial times 2. The 3 factorials reduce out, 2 goes into 4 twice, and I'm left with 10. So now I have 10 times 2x to the 3rd times negative 3 squared, right? Which is 10 times 8x cubed times 9, which is 10 times 72x cubed. That is 720x cubed. What is the coefficient of the x to the 3rd term? The coefficient is 720, not just the 10. When you have numbers here, your coefficient is not going to be only dependent upon that factorial expression. Number 3. Let's expand this one. Okay, x squared minus 2 to the 10th power. We want the coefficient of the x to the 14th term. You might at first say, wait a second, we're not going to have an x to the 14th term. The power here is 10. But we will, because this starts already at an x squared term. So, question, what do you raise that x squared to get to the 14th exponent? Well, when you have a power to a power, you multiply the power. So x squared to the 7th is x to the 14th. So we're taking the x squared that we start with, and we're raising it to the 7th to get that 14. That means this negative 2 is going to be raised to what power? 3, because those powers add to 10. So my binomial theorem tells me out in front I'm going to have 10 factorial divided by 7 factorial times 3 factorial. I come down here to take care of my factorials, and then I'll put it all together. So we have 10 times 9 times 8 times 7 factorial divided by 7 factorial times 3 times 2 times 1. Well, 7 factorials cancel out. And then we have 3 goes into 9 3 times, 2 goes into, doesn't matter, 8 4 times, and we are left with 10 times 12, which is 120. So, out in front, I have 120. Then I have x to the 14th. Then I have negative 2 cubed, which is negative 8. Okay? Negative 8 times 120 is negative 960. So that means that therefore, the coefficient is negative 960. All right? Okay, fun stuff. I love this stuff. Love doing the pattern. It seems like a nice break for us. Okay. If the entire expansion, if you only want one term, I will totally do it like this. If we're only looking for one single term, this is how I do the expansion. But if we are looking for the entire expansion, oftentimes it's easier not to use the binomial theorem, but to use something else called the Pascal's Triangle. Okay? This it's often faster. Okay, so by arranging the binomial coefficients in a triangular pattern, we obtain an array called Pascal's Triangle, named after the French mathematician, very famous mathematician, Blaise Pascal. There's his little picture. Let's see when he lived. He was young when he died. He was only 41 when he died. Anyway. Okay, here's how we get Pascal's triangle. I want you to start in the middle up on top, and I want you to put a 1. Okay? And then down below on the second row, on the sides of that one, I want you to put 1s right there and there. And then another 1 on the third row. In the middle, not a 1, we're going to add those two numbers together and get this right here, and that number is goes right there. And then on the sides is another 1. On the sides of the triangle are all 1s. And then to get any in-between number, you add the two numbers on above it. So 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. And we could just keep on going. It's kind of addictive, I think. Anyway, you get the idea. We could keep on going. I'll go one more. It is very addictive. 6, 7, 8. All right. So Pascal's triangle gives us the binomial coefficients. So the very first row gives us the coefficient of x plus y to the 0. The second row gives us x plus y to the first coefficients. The third row gives us x plus y squared, and so forth. I like to think of this, how I remember this is the power here, the power, you go to the row with that number in it. Go to the row with that number in it. And there's always only one row with that number in it. So if I wanted the binomial expansion for x plus y to the 7th power, I would go to this one, x plus y to the 7, because it has the 7s in it. And the Pascal's triangle is pretty quick to write. Pretty quick to write. Quicker to write than it is to multiply out a bunch of factorials. Okay, so let's use Pascal's triangle for a couple of examples. Let's determine the expansion of this. Okay. 1 over x minus 2 times y to the 5th power. All right, so I use Pascal's triangle, and I want to get to the 5th row, so it's quick to write, or I could flip the page, but it really is quick. I stop when I get to the row with the 5 in it. So I'm going to have 1 times 1 over x to the 5th power. And if you like, you can say negative 2y to the 0 power, if you like. That's just a 1, so you really don't have to, right? Plus, the next coefficient is 5, 1 over x to the 4th, negative 2y to the 1st, plus 10, times 1 over x to the 3rd, times negative 2y squared, plus another 10 times 1 over x to the 2nd times negative 2y cubed, plus 5 times 1 over x to the 1st times negative 2y to the 4th, plus 1 times 1 over x to the 0, of course you don't have to write that one, times negative 2y to the 5th. Okay? So this becomes, alright, so this is just a 1. So this becomes just 1 over x to the 5th. 1 to the 5th over x to the 5th. For our next term, we're going to have the 5 times 1 over x to the 4th times negative 2y. I'll simplify that in a moment. You know what? I might just go ahead and simplify it as I'm going. This will be a negative 10y over x to the 4th. Yeah? Next term, I'm going to have a 10 times 1 over x cubed times negative 2 squared is 4, and then y squared is y squared. So this becomes plus 40y squared over x cubed. Next term, plus 10 times 1 over x squared times negative 2 cubed is a negative 8, and then we have the y cubed. So this is going to be a negative 80 y cubed over x squared. Next up we have plus 5 times 1 over x times negative 2 to the 4th is a positive 16, and then we have the y to the 4th. So that will be 16 times 5 is 80, so positive 80 y to the 4th over x. And then our last one is 1 times negative 2 to the 5th. Negative 2 to the 5th is negative 32. And then we have the y to the 5th. So this is negative 32 y to the 5th. And that is the expansion of that binomial to the 5th power. Okay, another thing that we could ask you. What is the difference quotient of f of x is equal to 4x cubed? The difference quotient is a flashback to our very first unit of the year. The difference quotient is f of x plus h minus f of x all divided by h. The difference quotient is what we begin calculus with. Right after limits, we begin calculus with this. Alrighty, so f of x plus h, I'm putting x plus h in for x, so I'll have 4 times x plus h cubed. That is f of x plus h minus f of x. Well, f of x is 4x cubed, all divided by h. We need x plus h cubed. Well, x plus h cubed, I'm going to slide down, x plus h cubed, it's cubed, so I'm using those coefficients, 1, 3, 3, 1. So I'm going to have 1x cubed plus 3x squared h plus 3xh squared plus h cubed. What a quick expansion that used to take us forever Now it's a lot easier. Okay, so those are all equal here. Okay, I'm going to distribute my 4. I will tell you, you guys, when you are doing all of these terms, when you're writing a bunch of terms like we did above, in your final answer, make sure that you have the right pattern. Make sure you see the pattern with your x's and y's. Okay, you should see your x's, your first, whatever comes first, you should see that decreasing in power. You should see your last term increasing in power. Make sure that you have that pattern. That's one thing that you can do to decrease your little errors, your little, not really a typo, more of a right-o, your right-os. Okay, back to this. Our 4x cubes cancel out, and everything that is left has an h in it. Everything that is left has an h in it, so I'm going to factor out an h. I'm just going in there and I'm taking out an h. And now I can reduce my h's, and I get my difference quotient . I'm done. That's the difference quotient. In calculus, we'll take that difference quotient and we'll take a limit as h goes to 0. As h goes to 0, what does that become? 12x squared. That's the derivative of that function. Okay, let's do another one. The difference quotient of x to the 6th. Well, difference quotient is f of x plus h minus f of x, all divided by h. So f of x plus h is x plus h to the 6th power. We're subtracting f of x, which is just x to the 6th power, and we're dividing by h. Okay, I'm going to come off to the side because I need to do one more row of Pascal's Triangle. Up here I went to 5, row 5, and so I'm going to do one more row down here. I'm going to copy it down. Don't know if you can see it down here, but I'm going to copy it down. It's going to be 1, 6, 15, 20, 15, 6, 1. Okay, so I don't know if you could see me doing that, but I just did one more row of Pascal's Triangle. So when I expand this binomial, I'm going to have that. Those are my coefficients. So 1x squared, x to the 6th, plus 6x to the 5th, h to the 1st, plus 15 x to the 4th h squared, plus 20x cubed h cubed, plus 15x squared h to the 4th, plus 6x h to the 5th, plus h to the 6th. That's my very fast expansion of that very large binomial. Well, binomial to the 6th power, binomial to a very large power. And I'm subtracting x to the 6th, and then I keep everything the same. This row must be this row, so don't leave off your divided by h. Go ahead and write it. And now our x to the 6th reduce out. Everything else has an h in it. Everything else has an h in it. So imagine factoring out an h and then canceling out with this h. What's it going to look like? It's going to look like everything up here just loses an h. So it'll be 6x to the 5th plus 15x to the 4th h plus 20x cubed h squared plus 15x squared h cubed plus 6x h to the 4th plus h to the 5th. That's the difference quotient of x to the 6th. As h goes to 0, if we take the limit of this as h goes to 0, we would just get 6x to the 5th. Okay, one more example, and in class, I don't even know if I'll have time for this example. I just thought it would be fun to do one with an I in it. just also to review our exponents of I. So we have it to the 7th power, so I need to do one more row here of Pascal's triangle. So I'm going to start with my 1 on the outside, and then I add, so 7, and then 21, and then 35, and then another 35, 21, 7, and 1. It always reduces from there. There's symmetry there. Okay, so I have, fortunately I gave it to us where our first term is just a 1. So our first term is just going to be 1 to the 7th power, right? 1 times 1 to the 7th times I to the 0. I to the 0 is just 1. Plus 7 times I to the 6th, times 1 to the 6th, times negative I to the 1st, plus 21 times I to, I keep saying I, 1 to the 5th, times negative I to the 2nd, plus 35. I'm going to stop, well, no, I'm not going to stop. 1 to the 4th times negative I to the 3rd. I was going to say I'm going to stop writing 1 to the powers because that won't matter. But I'm going to write it out. 35, there's another 35, so 1 to the 3rd, negative I to the 4th, 21, 1 to the 2nd, negative I to the 5th, 7, 1 to the 1st, negative I to the 6th, and the very last term will just be a negative I to the 7th power. Okay, 1 to the 7th is just 1. So all of these are just 1s, right? So I'm going to ignore all of those now. All right. We're going to have negative to an odd power. It's going to stay negative. This is going to be a negative 7i, right? Here we're going to have, okay, a negative squared is going to be a positive, right? So it's going to be plus 21i squared. Okay, and now we have a negative to an odd power, so this one's going to be a negative 35i cubed. And then negative to an even power, that's going to be positive 35i to the 4th. And then negative 21i to the 5th. Okay, positive 7i to the 6th, and then negative I to the 7th. Okay, let's evaluate these i's now. So our 1 is still 1. I is still I. Can't get rid of that. But I squared is negative 1, right? I squared is negative 1. So this will be a negative 21. Yeah? What is I cubed? Do you remember the way Miss Houston taught it? She's the one who taught me this. Miss Houston did. I won. That's what you say when you win the lottery. I won. The middle two are negatives. So this is your powers on your I. Okay, multiples of your power on your I. I cubed would be negative I. So I cubed is negative I. So times negative 35 will be a plus 35i. I to the 4th is just 1. So I to the 4th is 1. So this is just a plus 35. I to the 5th. 5 is 4 plus 1, so you have a remainder of 1, right? So this is just I. So this is negative 21i. I to the 6th will be negative 1. So that's the second one over. So minus 7. And then I to the 7th will be negative I. That makes us a plus I. Okay, let's see if we can combine all of our like terms. So we have 1 minus 21. That'll be a negative 20. Plus 35 is positive 15. 15 minus 7 is 8. Okay? Negative 7i plus 35i. That'll be a positive 28i. Positive 28i minus 21i is positive 7i plus 1i is positive 8i, and I will be shocked if I did that right with my adding. But there's a way we can find out. Let's go to our calculators. Let me show you something on your calculator. Did you know that your calculator has a complex mode in it? Complex mode. If I go to mode and go down, do you see the a plus bi? Right now it defaults to real mode, of course, and then but you can change it to complex mode if you do. Go over here, turn that on. I'm going to go to my home screen, and I'm going to type this in as I see it. Parentheses 1 minus, and I want I. I is down here above the decimal. It's the blue above the decimal. So I'm going to do second and then decimal to get I. And then we're raising that to the 7th power. Let's see if I'm right. Oh, I'm right this time. Super, super easy to add wrong on those. Okay, so that is the binomial theorem and Pascal's triangle.